Hello, my dear students, and welcome back to the second half with this third chapter related to frequency measurement and spectrum analyzer. In the previous half, we have discussed together three different techniques that can be used to measure frequency. The first is depending on a counter and a timer. The second is depending on a PLL loop or phase log loop. And the final depends on bridge. Now, in this part of the lecture, we are going to consider the way or the instrument that can be used to display the frequency spectrum, or what we call the spectrum analyzer. So again, as we did in the previous chapter when we deal with the oscilloscope, the cathode ray oscilloscope, herein we are doing the same manual or the same procedure toward understanding what is inside an spectrum analyzer. A spectrum analyzer in general is a device that can be used to display the frequency domain, or what we can call the Fourier analysis of a signal. Considering the concept of the Fourier series, that any periodic signal is a summation of sinusoidal signals which have different frequencies, starting from a fundamental frequency up to the high frequency component. So using this concept, we can display the frequency response of different types of signal. We can do this either using an analog spectrum analyzer with the concept of Fourier transform, or maybe using the digital spectrum analyzer using the concept of FFT or fast Fourier transform. Maybe in this lecture, we are going to focus more toward the analog spectral analyzer, because as you know, we are still in the analog portion of our module under the analog measurements. So what is an analog spectrum analyzer? Or in other words, what are the main building components for a analog spectral analyzer? This is the whole block diagram for a spectral analyzer. But before starting from the input side, let me start back from the display side. So as you can see here, the displaying concept of the spectrum analyzer is typically the same as an oscilloscope. If you remember, in the oscilloscope, we need this triggering signal in order to trigger or in order to sweep the x-axis from the extreme left point to the extreme right point. Typically the same here. However, the sawtooth or the trigger signal here is more representing the frequency rather than the time. So what is displayed on the x-axis here is the frequency of the signal. Now let's see the main component for the spectrum analyzer. First, we have our input signal, and then our input signal is pre-filtered. Usually we use this pre-filter, which is typically a low-pass filter, in order to get rid of any high-frequency component noise. As you know, here we are dealing mainly with frequency. So having imposed high frequency component noise can affect our measurements. That's why we have this pre-filter as a low-pass filter. Then we have the mixer. The mixer is mainly a multiplier between the input, what we can call between brackets in the communication terminology as a baseband signal, and our local oscillator. The main concept of this mixer, as we are going to understand later on in the slides, is to upgrade the frequency from the baseband signal to the intermediate frequency signal. Herein, you can see that we have an intermediate frequency gain unit, an intermediate frequency filter, again, in order to filter the component targeted, and then we have this log amplifier, and finally we have the detector that detects or that display using the video filter the impulses representing the targeted signal. This is the general block diagram of our spectrum analyzer. So let's go into details how this block diagram is used in order to display the frequency of a signal. Let's start with the first stage, which is the mixing stage. And I believe that this mixing stage, you already know it deeply from your analog communication class, because this is typically the same as what you did in the analog modulation. When you multiply the frequency of the signal, so let's assume that this is between quotation the message and this is the carrier. Here we have the same methodology. Here is the frequency of the signal and here is the local frequency of the oscillator. So multiplying this by this, we will get two harmonics. We will get F local plus F signal and F local minus F signal. Here is the F local and here is the F signal. So this is these two sides of the or these two impulses are the main output of our filter. Then using the intermediate frequency filter, you can select one of these two signals or you can select both of signals. So you can here control the input frequency filter in order to display either you can display this one or you can display this one or you can display both signals. Then here we go to the detector where we detect or where we make the variation into the signal. So this is the concept of the job description of the detector here. The main issue that appears here is simply what we can call the background noise. So if you can see here, this is our impulse, but our impulse is mainly surrounded with a lot of harmonics, high frequency, low amplitude signals in the right and in the left of the impulse. So in order to make a smoothing process, we use our video filter so that we can turn this into this. So finally, this is the overall block diagram of our spectrum analyzer, starting from the signal up to the display. As you can see here, my dear students, that we use here this infrared gain in order to control the amplitude of this signal. So sometimes when you have a very weak signal, the amplitude here is relatively low, so you can control the amplitude here. And also we already discussed this later on, earlier in the lecture when we consider this sweep generator or this trigger in order to display. From the frequency point of view, you can see here this diagram. So this is the input frequency, this is F signal, and this is the F local oscillator. After the multiplication, you get these three peaks. So you have F local oscillator, and you have F local oscillator plus F signal, and you have F local oscillator minus F signal. And now you can typically control the display. You can control the display from 2 points of view. First, from the filter point of view. So based on the bandwidth of this filter, you are going to control which of these impulses or which of these delta Dirac functions, hypothetically, or what we can call pulses, in a real world, which of them will appear. The second is whenever your sweep will start. So if you start sweeping from here, though this is the starting of, this is the extreme left point here, which is this point. This is the extreme left point. So in this case, what you will see is this, which represents the positive frequency side. So as you can see, you see here 50% or the right-hand side of the local oscillator frequency, this one, and you see the F local plus Fs, this one. This is what you see because this is the extreme left point and this is the extreme right point. And then you have your frequency spectrum appear on the signal. Again, this is finally the output. This is our output. So this we have here the input. This is a keyboard to control the bandwidth of your filter, and we have our trigger. And again, you can use here external or internal trigger based on your needs. That's all for the spectrum analyzer. Thank you very much, and waiting for the next chapter, inshallah, chapter number 4, dealing with analog noise. Thank you very much, and see you later on.